In episode 1, we learned that semiconductors are the smart middle ground between conductors and insulators. But how do we take something as common as sand, turn it into the most complex objects humanity has ever manufactured? Every smartphone, AI system, and computer begins as simple silicon dioxide. Today, we go behind the clean room doors to witness the extraordinary engineering journey that transforms raw earth into the microscopic logic of the digital age. So why silicon? It isn't just because it's the second most abundant element in the Earth's crust. Silicon holds what we call functional supremacy. At its core, silicon is a microscopic electrical switch. It maintains its structural and electronic integrity even under extreme temperature variations and physical stress. It is this thermal stability that allows your devices to run high-performance tasks without melting the very circuit that power them. The transformation begins with a violent chemical reaction. We take sand, rich in silicon dioxide, and place it in an electric furnace at a staggering 2000 degrees Celsius. By adding carbon, usually as carbon coal, we force a process called reduction. The carbon literally strips the oxygen away from the silicon dioxide. The oxygen flows away as carbon monoxide gas, leaving behind raw, molten silicon. The chemical equation is simple, but the environment is extreme. In the reaction, silicon dioxide reacts with 2 carbon atoms to produce silicon and 2 carbon monoxide molecules. As raw silicon is a start, but it isn't ready for tech. Electronics require electronic-grade silicon. In this industry, a single foreign atom can short-circuit a device. Purity is non-negotiable. So we use a 2-step molecular transformation. First is chemical gasification. We react the silicon with hydrogen chloride to create trichlorosilane gas. This leaves all solid impurities behind. In the second step, thermal decomposition. We then decompose that gas with hydrogen to recover ultra-pure silicon. Next, we must forge the ingot, a massive solid cylinder of ultra-pure silicon. This follows the single crystal mandate. The atomic structure inside this cylinder must be a single continuous lattice from end to end, without any boundaries or fractures. Any disruption in this crystal structure causes unpredictable electrical resistance. Perfect uniformity is the only way to guarantee the reliability of the billions of components we are about to build. Now comes mechanical precision at the micro level. The ingot is cropped, ground into a perfect diameter, and then sliced into thin discs called silicon wafers, often only fractions of a millimeter thick. Finally, we polish the wafer to a mirror-like finish to ensure an incredible smooth surface. These are the industry blank checks. They are unprocessed and contain no circuits yet, serving as the foundational base for all subsequent processing. Size matters in the semiconductor world. Early tech used 4-inch and 6-inch wafers. Today, 8-inch wafers are mainstream for consumer electronics, while the 12-inch wafer is the modern advanced standard for AI and high-performance hardware. Let's look at the hierarchy of what we have built. The wafer is the base material. The dies are the individual rectangular units created by dicing a complete wafer. The chip is the final process component containing millions or billions of logical elements like transistors and resistors. The final device manufacturing involves back-grading to thin the wafer for compact devices, CMP polishing for extract tolerances, dicing into individual units, and packaging the fragile chips into protective casing. The entire process happens in massive, multi-billion-dollar facilities called foundries. Today, Taiwan stands as the ultimate global hub with TSMC, Taiwan Semiconductor Manufacturing Company, leading the world in high-performance silicon processing. Understanding manufacturing means understanding the technology that powers our future. If you want to master the concepts, like, subscribe, and DM me to receive your free semiconductor fundamental notes from today's episode.